Okay, so he did his PhD at the German Electron Synchrotron Facility and at the Friedrich Alexander University in Erlangen, Nuremberg, studying ultra-high energy neutrinos with radio detection, with radio detectors. And then in 2022, he moved to the University of Chicago and became a fellow at the Kavli Institute for Cosmological Physics, again on the same topic. Okay, I will hold it. There it goes. Okay. Anyway, I'm sure you will hear more about this, but his field is detection of ultra-high energy neutrinos with radio techniques. He's going to talk to you about how astrophysicists see the universe. I wanted to make one aside about this Kavli Institute for Cosmological Physics. It was actually founded a little over 20 years ago as the Center for Cosmological Physics, and the founding director who pulled the group together was a physicist named Bruce Winstein, who unfortunately died a little over 10 years ago. And he gave the very first Compton lectures in 1972 on sort of the expanding field of particle physics at that time. So I was going to bring a picture which would give you a glimpse, which most of you remember what things were like in 1972. But anyway, there's a nice continuity with that. So, Christoph.
Okay, does this microphone work better?
Very good.
Good. Okay. So yeah, great that so many people came. So what I want to talk about is, well, how do we, as astroparticle physicists, see the universe? Because if you want to do astrophysics, there is this problem that probably no other science has, and that is that basically everything you want to study is really far away. So this is just one example. This is with the new Euclid telescope that was launched like half a year ago. Almost everything you see in here is an entire galaxy. And it's billions of light years away, and if you want to study this, all you can do basically is look at it. You cannot influence it, it's just going to do whatever it wanted to do anyway, and you just have to be really good at looking at this to figure out what it does. And so what do you use? Of course, telescopes, right? And right now is a really good time kind of to be an astrophysicist, because we got a lot of really cool new telescopes that either have just launched or are about to have what's called first light, when you kind of switch it on for the first time. If you're kind of the kind of person that likes to go to events like this, you probably heard about the James Webb telescope that was launched a bit ago. Also recently, this Euclid telescope that you just saw this picture from. These are two infrared telescopes that are going to look back way to the very early times in the universe. You also have ground-based telescopes, for example, the Very Large Telescope that we're going to talk about a little more later. That's already something like 20 years old, but it still gives you really precise, pristine pictures of stars, galaxies, all that stuff. And then later this year, we're going to have the Vera Rubin Observatory, which is kind of different than what you would normally expect a telescope to do. It's not really there to give you like a very good, precise picture of a specific object, but it's just going to look at a really big part of the sky, and it's just going to look at the sky repeatedly to look for what's called transients, which is just basically when something in the sky changes, when we have, for example, a supernova or something. And with this way, we can see these changes in the night sky. And of course, you get a lot of really cool pictures. You saw this one earlier. And for example, from the James Webb telescope, you can see this really cool picture of the Crab Nebula, which is, this used to be a star that exploded about 1,000 years ago. We know pretty precisely when it exploded, because some Chinese astronomers actually saw it and wrote it down, and later astronomers found it again. And it's a really interesting object that we're going to talk a lot about later in some future lectures. But I felt there was kind of something missing in kind of how this stuff gets reported, because usually it goes, some new cool telescope is launched or it's built, and you read about this. Then you see some really cool pictures, and then you read about a discovery, but in the discovery, well, you see a picture like this that, well, is very clearly CGI. So this is obviously not what the astronomers actually saw, right? So if you track down the paper, so this is, by the way, about something called a white dwarf that's probably going to explode fairly soon. You can probably see it by eye. Probably not in Chicago. So, like, what does it actually look like? If you track down the paper, it looks like this. It's not as pretty, I guess. But if you know what this is, and if I do a good job with these lectures, in a couple of weeks you will know what this is. This is actually really interesting. So that is what I want to talk about, basically. Oh yeah, also, there's a bunch of stuff that we use that is not really like your classical telescope that gives you these pictures. So you have, okay, these look kind of normal, I guess. Your radio dishes, but you can actually connect these together and kind of pretend you have a much bigger telescope than you actually have. Or you actually don't need the dishes. This is something called LOFAR, which is in the Netherlands, and then there's a couple others like this in other parts of Europe. You can just kind of connect these and almost build a telescope like the size of Europe, more or less. And it doesn't look like much, but it's actually for these wavelengths it's looking at, it is one of the best telescopes in the world. Now you have this thing called HESS, the High Energy Spectroscopic something. It looks like a normal telescope, but it's not actually looking at stars. It's just looking at the atmosphere. And it's trying to find high energy gamma rays that are coming from space. And we use that. Or there's this. This is basically a water tank with some fancy electronics in it. Use this to look for cosmic rays in Argentina. Or you can go to the South Pole, you put a bunch of basically just light detectors in the ice, so you look for neutrinos. And then, of course, you have LIGO, which is you just look for kind of space itself changing, contracting, and expanding. And I also want to talk about basically how all these works and what they can tell us. So this is what I want to talk about, and basically the question I want to answer is, how do we actually measure stuff in astrophysics? So we're going to pretend that we understand the physics as it is here on Earth, and now we want to see, okay, how can we apply this to astrophysics and figure out what's going out there. So today I'm just going to talk about, give a little bit of an introduction and talk about how telescopes work. Then next week we're going to talk about spectroscopy, where we're just looking at what different wavelengths of light we get from a source and what all the stuff that can tell us. Then after that, I want to talk about how do we actually know how far away that star is or that galaxy or whatever's out there. And then next, we're going to talk about microwave and radio astronomy, where we're not using visible light, but we're using, I guess radio, obviously, and something that's like slightly higher frequencies. And then I want to switch gears a bit, because all this is basically just using light. But there's a bunch of stuff that I just showed that doesn't actually look for light. And that can also tell us something about what's out there. So there are these cosmic rays, which are particles that fly through space. They sometimes hit the Earth or the atmosphere, and they can have energies that are almost 1 billion times as much as anything we can produce here on Earth with particle accelerators. And we still don't really know where they're coming from. Then next, it's going to be about gamma rays, which is still light, but it has so much energy, it has such a short wavelength, that it actually kind of acts very different from like your visible light. Then I want to talk about neutrinos, these weird particles that tend to not interact with this, which is both a blessing and a curse if you want to use them for astrophysics. And then finally about gravitational waves, where we look at what space itself does. So that's the plan, but today I want to talk about telescopes. And you could argue that modern astronomy or astrophysics kind of started with the telescope. Of course, there were people looking at the stars basically probably since mankind existed. But the kind of a big deal was when this guy here, Galileo Galilei, heard that there were these people in the Netherlands that were usually making reading glasses, but they invented this cool new thing called the telescope. And he basically bought one from there, figured out better ways to produce one, and made his own one here that was had a better magnification than things you could buy in the Netherlands at the time. And he went to the Senate in Venice and showed them this, and Venice at the time was a big trade empire, and that meant they were really rich. And of course, they didn't really get there by always being nice to people. So if you were a sailor and you could see if a ship was someone you probably should keep away from, that was really useful. So They were impressed, gave him a professorship in Venice, and he worked as a researcher there. And of course, he used it to look at the sky. And he looked basically at pretty much anything he could see. And one of the things he noticed was he looked at Venus, and he saw that it had phases, kind of like the moon. So this is one of his drawings. And it's, this is basically like what the moon looks like some of the time. But at the time, of course, most people believed believed in this geocentric model. And it didn't really make sense because the model said that Venus should be, can you see this dot? Okay. Venus should always be between the Earth and the Sun, so there should be no way you can see all of it illuminated. So, okay, something must be wrong here. And he saw another thing. He looked at Jupiter. This is with a modern telescope, so his picture was not as good. So he saw Jupiter, okay, but then he saw these, at the time he only saw 3 of these other, what he thought were stars, that were all in a line, which, okay, was kind of odd, but, it could just be a weird coincidence. Sometimes stars are just in a line. But then he looked another day, and he saw that these had moved. And these are actually his drawings. So he saw them, 2 of them on one side, then he saw 2 on the other side and 1 there. And they just kind of kept switching sides. At some point, he saw a fourth one. So these are called the 4 Galilean moons, because he was the first one to see them. And his conclusion was that, well, they, if they're all moving this way, they must be orbiting around Jupiter. And so this was kind of the first time you had you could directly see something orbiting something that is not Earth. And of course, that got him to claim that the Earth was not the center of the universe, which famously got him into a lot of trouble with the Catholic Church. And I don't want to defend this, but I think it always also gets kind of oversimplified. It is always talked about as, how did they see that it's so obvious that, the heliocentric model has to be right. But there was a big problem with the heliocentric model at the time, and that was it didn't work either. Because at the time, with the heliocentric model, everyone assumed that, or the models that were available at the time all assumed that all the planets move in perfect circles, and they always move with a constant speed. And if you put that into your model, you calculate where should I see these planets, it didn't work. It predicted them to be in places where they obviously weren't. And one of the people that tried to solve this problem was this guy, a Danish astronomer called Tycho Brahe. He was hired by the Duke or King in Prague to be his astrologist, as they were called, unfortunately, at the time. And he did one thing better than basically anyone else in the world at the time, and that was just measuring where the stars and the planets were. And so he built this giant catalog of star observations. And that's actually something we still do today. So this is something called the Gaia mission. This was a satellite that was launched almost 10 years ago. And it's basically just measuring where stars are. It's measuring the distance. It's measuring how bright they are, what color they emit light in. And it's just compiling a big data set and just basically dumping it out there. And it's very useful for a bunch of people in astrophysics. So basically, some things haven't really changed in 400 years, or almost 500 years, I guess. And then next, there was this other astronomer called Johannes Kepler, and he was also went to Prague to work with Tycho Brahe. Unfortunately, Brahe died about a year after the two actually started working together, so that didn't quite work out. But Kepler inherited this whole catalog of observations that Brahe did. And this is kind of a good example of this connection between observation and theory. So Brahe is kind of like the stereotypical observationist. You just try to measure stuff, and then Kepler tried to figure out what it all meant and tried to come up with a good theory about this. And he came up with something, a pretty good explanation of why the stars are, or the planets are, where we see them. And he found out that if you just make 3 propositions, and you calculate, where should I see the stars, then they are where they are. And first thing he changed was, well, actually, the orbits are not perfect circles. They are ellipses, which are these kind of like slightly elongated circles. Now, this is greatly exaggerated. The actual orbits are pretty close to circles, but not quite. Then he found out that they're also not moving with a constant speed. When they're closer to the sun, they actually move a bit faster than when they're further away. And he actually could quantify this pretty precisely. He could say that if you were drawing a line from the sun to where the planet is, and then for some time you basically pretend, you're drawing this line along, and you could just color everything in that the line goes over. Then over the same time, you will always have the same area covered. So if it's close to the sun, this line is shorter, so the area it covers is is a bit smaller, but it's also going to move faster. If you're back here, it's going to move slower, but you have this wedge here is much, much longer. And then lastly, he found out that if you compare the orbits or the time that the planets need to go around the sun, and you compare it to the distance, then if you take the orbital period and you square it, then it's proportional to if you take the distance and cube it. And he could show that if you just assume these three things are true, then you get and you calculate where should I see the planets if they are true, they are exactly where he saw them. And an important thing to note here is he had no way to measure the distance to the planets. This was just simply not possible. So this is actually not something he could not directly measure what the distance between a planet and the sun was. All he could show was that if you assume these are true, then as far as we can tell, the world looks exactly as we would expect it to be. And that's kind of the big thing you have to swallow a lot of the time in astrophysics. A lot of the time, you're not going to be able to see everything you would like to see. You just can, you have to build your model. You have to calculate what would I expect to see, and then you hope that that's actually what you see, and then you try to verify it. Or you have to do it the other way around. You see something you don't understand, and then someone has to build a model to try to explain it, and then you try to make predictions. But unfortunately, a lot of the time, a lot of the stuff is just not going to be observable to us. Then next, I guess, hero in our story is Isaac Newton, arguably the greatest physicist to ever live. And he did a lot of stuff, but the important part here is, first of all, he found his 3 laws of motion. The first one is that if you have an object, and if it's not moving, it will not just spontaneously start moving. And if it's already moving, it will just keep moving with the same speed in the same direction, unless you apply a force to it. Then, what is this force? So here we found this simple equation. That is, if I have an object with a certain mass and I want to accelerate it by some quantity, then you just multiply the mass and the acceleration you want to calculate what force you have to apply to it. Fairly simple. And then lastly, if you apply force to something, it will apply a force back to you. So, if you push something, it will push back against you with the same force. And he also found this theory of gravity that just says that if you have 2 objects that have a mass, then they will attract each other, and you can calculate the force that you have from here, that you get from that, by just multiplying the 2 masses times this constant, and then you have to divide by the distance between them squared. Now, the interesting thing is that he could show that if you assume these 4 propositions here are true, you actually get Kepler's laws back. And he could also show that if you assume these are true, then objects on Earth should fall exactly as we see them fall. So that's kind of a big deal, because it shows that actually you can apply the exact same laws of physics that we can see here on Earth to the stars, the planets, and all that, which is not at all obvious, right? Like hundreds of years before him, there were all these models where you have like these big glass spheres that the planets are traveling on, and you could just say, oh no, you just need the laws of nature as we see them on Earth. And that is just something we have to kind of assume if we want to do astrophysics, because as I said, a lot of the time we cannot see everything that we would like to see. So we have to take the laws of physics as far as we know them, build our models, calculate what we should see if this is whatever is out there is what we think it is, and then we can try to verify this. And of course, if we want to verify this, we use telescopes. So I guess the rest of today I want to talk about how telescopes work. So to get started with this, we should first get a good idea of what actually is this light that we're trying to measure. And you look it up on Wikipedia or something, it will tell you, okay, it's an electromagnetic wave. So okay, that explains something, but what does it mean exactly? So it's fairly simple. The electric force just means if you have two particles or you have two things that have a charge, then these will attract each other. If you have different charges, or if they have the same charge, they will repel each other. Okay, so far so good. Now what we can do is we can ask, okay, I have some charges here. Let's say I have two charges here. If I now put a third charge somewhere, what force would be applied to this charge? And then I can calculate this, and I can draw something like this, where I just draw an arrow everywhere that points you to the direction that this charge will have a force applied to it. And then if you do this, this is basically what an electric field is called. What's called an electric field. It's just basically calculating what forces would be applied to a charge that was at a certain at a certain position. But now I can do something else. I just don't have my charges just sitting there. I just take one of the charges and I just kind of wiggle it a little bit. If I do this, I find something interesting happens, and then that is that a little time later, if I have a second charge somewhere, it will also start to wiggle a little bit. So wiggling one charge will just apply force on another charge. And if I try to then draw this electric field for this, it will look something like this. So I have my arrows that show me where, if I had a charge here, what force would be applied to this. But now, the force changes. And it's, you have this field like slowly wiggling its way towards the other charge, and when it reaches it, it will start moving this one. And this is a slightly simplified version of what exactly light is. Now, the big question is, okay, like how fast do I wiggle this charge? Because that basically, how fast I wiggle my charge is basically the frequency of this electromagnetic wave, and that kind of tells you what kind of light you have, or what's called the electromagnetic spectrum. So if I have, your favorite radio station is probably going to have something like 100 megahertz. So that's 100 million times a second I have to move this charge. I probably cannot, move my arm that fast. But what I could do, I could just, for example, just take a big metal pole, I apply two electrodes on the sides, and then I just run a current through it that goes back and forth 100 million times per second. And if I do that, then I basically built a very simple radio antenna. And if I, cramp up the frequency, at some point I can't actually do it with an antenna anymore. I have to use other processes. But if I just wiggle faster and faster, then eventually I go to microwaves, to infrared, to our visible lights, to the UV light that gives you sunburns, maybe. And eventually you can get X-rays and even gamma rays. Now, another important relationship is between the frequency of this wave, so how fast I wiggle my charge, and the distance between the two maxima of the wave. So how long is the distance between this this part of the wave and this part? That's called the wavelength. And that's fairly simple. That's just you take the speed at which the wave moves and divide it by the frequency. So if you have a very high frequency, you have a very short wavelength. If you have a very low frequency, you will have a very long wavelength. Okay, now another very important thing that's going to come up again and again and again in this lecture. So if you just want to remember one thing, it's probably this. And that is if you have two waves. So in this, I have my wave here coming in from the right, and I have a second wave from the left. If that happens, they will just move through each other and just kind of go the separate ways. But they will interfere. That means that if I have my charge here and I try to figure out what forces applied to it, I will get the sum of these two waves. And you can see that in some places, they amplify each other, but in some places they will just cancel each other. And that is something you can see pretty nicely thanks to these two guys. So water waves are more or less waves, and you can see if you just follow like one of these rings, they just kind of they don't care about the other waves there. But you can also see that there's some places where you basically where they cancel each other out, and some places where you get a maximum, and that is going to come up again and again and again. So keep that in mind. Okay, hang on. It doesn't want to. Okay, now something that happens is usually with these waves is that you don't have just one thing emitting waves, but you have a bunch of things. But as we just saw, I can just I just can treat the wave from each of these ones. So each dot here is emitting a wave. I can just take the wave from each of these emits separately. I can just calculate, okay, what does this one do? And I do this for all of them, and then I just add them up. And what usually happens with these is that if you go really far away, and if you're doing astronomy, chances are you're really far away from the stuff you're looking at, then you get these wave fronts where you have all this weird interference here, but if you're far enough away, you kind of have these very nice wave fronts where you just have, you can imagine you have like a bunch of these sine waves just moving like all next to each other along here, right? And if these waves then go through medium, so for example water, they will slow down a little bit. So that's if you put a straw in water, you see this weird bendy thing. And what's causing that is basically you can see here you have your waves coming in from the left, and they come here and they hit the water here, and they slow down. So first thing you see is now the wavelengths are shorter because they're moving slower. But the other thing is that if you look at just one individual wave, it still looks like it's moving to the right. But if you kind of squint so you can't see them individually, you just see these like blue bars. Now it looks like they're moving to the side. Like it looks like they're changing directions. So, right? Here they're moving this way, and now they're moving that way. And because it's often kind of annoying to always draw these wavefronts, what we often do is we just draw these rays. We use what's called ray physics, where we just draw the direction that these wavefronts are moving in, because then you just have to draw one line instead of all this stuff. Now, because our light changes directions, I can use this to build a lens. So what this is basically is, I take my glass. I have a glass surface that's bent. So if you have your light coming in from the left here, it hits the surface and it gets bent inwards a little bit, and then it goes to the air, and it's again bent a little bit. And if I give this this glass object the correct shape, then what will happen is that there is some distance called the focal length where basically this entire wavefront is going to get concentrated in one point. And if I can then just kind of put, I don't know, like a CCD sensor or something here, or I can just put a screen in here and then I have kind of a projector, or I can just have a like slightly transparent screen, and I just take take my magnifying glass to look at it, and then I have a bigger picture of this, of whatever sends the light there. But you see that, now that I look through this glass, actually, this, if you follow this ray, like where's it coming from? This is actually coming from the same, like it doesn't have to change direction from the screen. So I actually don't need the screen, I can just move it away. And it's just going to guide this ray into my eye, and it's also going to guide this ray into my eye. And that's basically what a simple telescope is, or what's called a refractor telescope, where you just have two lenses. But there's a problem with refractor telescopes, and that is that this index of refraction, which is basically by how much the light slows down, that depends on the wavelength. So for green light, it's going to be different than for red light. And this is, our guy Isaac Newton that we saw earlier. He actually did some experiments with this, and you can see what happens then if you take a prism, for example. You get this rainbow thing, right? So that's kind of a bit of a problem for our lens, because it means that the distance from the lens where all our light gets focused is going to be different for different wavelengths, right? So if I now want to put my sensor or my screen somewhere, well, where do I put it? I cannot have all of them in focus. And this is something you're going to see actually come up in photography sometimes. So here's, a picture of a leopard, I think. And if you look, cheetah? Oh, okay. Okay, good. That's why I'm a physicist and not a biologist. Okay, but if you look at kind of the side of this, you can see this like kind of greenish fluff here, and you can see that here it's kind of reddish. And that is because, you cannot focus both the red light and the green light here. And this is also something that happens in our eyes, because, we have a lens in our eyes. And that also has chromatic aberration. So if you look at, this very great text, you know to never do this, because red text on blue background is always hard to read and it just feels awful. That is because your eyes cannot actually focus both the red light and the blue light at the same time properly, which usually doesn't really come up much, but this is kind of because the edges of this, for example, this T, right? Do you focus on the red part of the edge or on the blue part of the edge? You cannot do both, and that's why these always feel kind of weird. So instead, what you basically almost always use in astronomy these days are these mirror telescopes, because if you have your light coming in from here again, and you just put a mirror that's a bit bent, it has kind of a parabolic shape, it will still reflect, it still reflects the light inwards and focuses it on a single point. But the great thing about mirrors is that the direction they reflect in does not care about the wavelength at all. So you do not have this chromatic aberration in there. So today, pretty much all big telescopes for astronomy are these reflector telescopes. Now, you can see from this drawing that actually, if you had just had this mirror, the focus where all your light gets concentrated would be back here. And in principle, you could put your sensor or your screen or I guess your astronomer back here. But the problem is if you do that, it's gonna, if you have a big apparatus here, that's gonna block a lot of the light. So usually what you do is you put a second mirror somewhere in there that then either pushes it to the side, or a lot of the times it will just reflect it back here, and then you have a hole here in the back where you then can put your sensor. So that's kind of the basic principle how telescopes work. But then there's a second aspect you have to think about, and that is, well, there's not just visible light, there's all this other frequencies or wavelengths of light. And the stuff that we can see is actually only, this tiny little fraction of it. And of course, you will probably want to use all of it, and we're going to talk about a lot of this. So today, in the next 2 weeks, it's mostly going to be about ultraviolet, visible, and infrared light, because in practice, those tend to be kind of work very similarly. Then after that, we're going to talk about all those radio wavelengths, and in 5 weeks, we're going to talk about gamma rays. If you're a fan of X-ray astronomy, I'm very sorry, I have to skip that one. I can't talk about everything, but it's also used quite a lot in astronomy. But if you want to do that, and what wavelength you choose is going to change a lot what you're actually going to be seeing. So this is this Crab nebula that I that I showed a picture of earlier, this star that exploded 1,000 years ago. If you're wondering about the name, this is what William Parsons, one of the first people to observe it, thought it looked like, and someone decided that this looked like a crab, so that's where the name came from. And so if you look at it in radio waves, it looks kind of like this. So radio waves will show you, for example, it will show you particles that are moving, that are getting accelerated. It can move you. It can show you certain types of hydrogen in some situations. And infrared is really useful because it tends to be really good at looking through dust. For example, if you want to look at stuff that are kind of near the center of the Milky Way, if you use optical light, a lot of it is just going to get blocked by dust. And a lot of the time, infrared radiation, will let you let through this. Then, well, visible light is visible light. That's what you would see with your eyes. That's still probably like one of the most used wavelength, because, for example, our sun, it is actually the most intense invisible light. It's not surprisingly, because like evolutionary, right? It makes sense that we evolved to see the light that is most common. If you use ultraviolet light, you can see tends to be good if you want to see like really hot things, because the hotter something is, the more UV light it will emit. Then for X-rays, you can see, for example, you suddenly see that there is this thing in the middle of it that's called a pulsar. That's kind of spinning extremely quickly and accelerating particles, and you can basically see products of this particle acceleration. And then finally, X-rays will tell you about like the really extreme phenomena in the universe. And we're going to talk in more detail about all this stuff that's going on in the Crab Nebula in a couple of weeks. But depending on what wavelength you want to use, you're going to run into a problem, and that is that if you want to build your telescope on Earth, you're going to have the problem that a lot of this light is actually not going to make it through our atmosphere. So this is, this brownish area tells you kind of how much of the light gets blocked. So if it's up here, basically nothing gets through the atmosphere, and if it goes down, then at least you have some part. And it turns out actually most of the electromagnetic spectrum just gets completely blocked. So you want to see something in UV or gamma rays, yeah, that's not going to happen. So really from Earth, the only thing you're really going to be able to easily see is radio waves, visible light, and then some infrared light. And of course, that's why we have telescopes in space. So you can obviously build telescopes in space, and we have done this. The problem is they get really expensive. Putting anything in space is extremely expensive. So just for comparison, so this is the James Webb Telescope, which cost $10 billion, roughly. It's maybe not a fair comparison because it kind of famously went way over budget and was a bit of a mess. But if you take a fairly small telescope like Euclid, that's already $1 billion, so that's still not cheap. Compared to like one of the maybe not like the biggest telescope, but a really good telescope, the Gemini telescopes. There are two of them, one in the northern hemisphere, one in the southern hemisphere, so you can see both parts of the sky. That gives you two telescopes for about 190 million. So you're an entire order of magnitude less. So you really, these days, you really only build space telescopes if you want to see these wavelengths that are not going to make it to the Earth, because otherwise, it's just going to be way too expensive. And the other thing is space telescopes also have to be a lot smaller, because you cannot just, you can only strap so much stuff to a rocket. So if you look here, these are our space telescopes. James Webb is gigantic for a space telescope. Hubble is actually not that big. It's something like 2 meters of mirror. If you compare this to stuff that we're building on Earth, it's an entire different world. So these are the Gemini telescopes. This is currently getting built in Chile, and it's you can see here for a comparison, it's more than the size of a basketball court, and there's just no way you're going to build something like this in space. So that's why today you only build space telescopes if you if you really have to. And I say today because there used to be another good reason to build telescopes in space, and that is that the atmosphere does a lot of other things. And one thing that was a really big problem is something called seeing. So you can see here someone pointed a video camera at the moon through a telescope, and you can see that it's kind of flickering. This is also why the same thing that makes stars kind of seem to flicker. And what's happening is that you have your light coming from space, and it has these really nice straight wavefronts. But then it's going to hit the atmosphere, and there's going to be wind. There's going to be a lot of stuff going on in the atmosphere that's going to cause turbulences, and then that's going to mess up your wavefronts. It's going to kind of change. It's going to change the directions very slightly of the light. And you can see this here pretty well. Now, if this is the moon is really bright, so you can easily take a photograph or take a video like this. If you want to look at a really faint source, you're going to have an exposure time of sometimes several days. So instead of just seeing this nice little movie, you're just going to have this all washed out. So it's all going to be really blurry. Fortunately, there's a way around this, and that's called adaptive optics, which you probably have seen this picture where you have these telescopes and then they have this laser shooting at the sky. This is what it looks like in detail. It's sometimes you see it kind of in the middle here. These ones are 4 lasers that are on each side, and what's it doing is it's gonna put a little orange dot on the sky, and you know that this has to be a very small dot because your laser is pretty small. But now what you can do is you point your telescopes so that both the thing you want to actually look at and this orange dot is both being recorded. Then you have this secondary mirror. You have your big mirror like somewhere here, but then that gets onto another mirror, gets reflected here, and then you have this beam splitter, which is basically a plate that is going to reflect a little part of the light, but most of it is just going to pass through. And most of the light is just going to go through your camera, whatever you have in the back of your telescope to record the image. But part of it is going to get split up into this wavefront analyzer. And what that's going to do is it's going to look at this little orange dot that has to be this tiny little dot, and it's going to look at, okay, what does this actually look like? And from what it should look like and what it actually looks like, it calculates, okay, how is my picture being disturbed? And then you have this mirror that's, for example, this is for the Very Large Telescope. And this has a very, very thin thin surface. And behind this are these little things. Those are tiny little electromagnets. And they will deform this little mirror so that it corrects whatever the atmosphere did to our picture. And these are just some more pictures. So this is kind of the thing that these little actuators, that's what they're called, to go into. And then this is what it looks like assembled. And this can really improve what the picture looks like. So this is, on the left, this is what it looks like without this adaptive optics. If it also already looks pretty good. But then if you zoom into this tiny little part, then suddenly, stuff starts looking blurry. That is because of the seeing. So if you apply adaptive optics, now suddenly you can see all these tiny individual stars. And that was about 20 years ago. This was a really big deal because, as probably know, Hubble was launched before this. So one of the big motivations for Hubble was that you do not have to worry about the seeing. And this basically gave us an alternative to having to launch everything into space to get a good picture. So, okay, now we have our nice, crisp light points all focused somewhere, but you're actually only halfway done. This is something that kind of gets overlooked a lot of times. A lot of times you read about like these big telescopes, but actually there's telescopes and then there's instruments. Instruments is kind of what's behind the telescope, what actually then measures this light that the telescope focuses. So the telescope is really only there to just focus your light at one point. And then you just have, usually you have one telescope and then you have a bunch of different instruments behind it that will all do different things. So for the very large telescope that we just saw how it uses these adaptive optics, just as an example, there's actually 3 different ones that are all, pretty huge. So there's a guy for comparison. So one thing you have here is something called the hawk eye, if you combine these letters. Now that's for infrared light, and this is, for example, if you want to have a relatively large field of view. So you're not only interested in this one particular thing, but you just want to see a somewhat larger part of the sky, but you're okay with if each individual thing in that part of the sky is maybe not imaged as well. Then you have something that actually doesn't give you a picture. That's something called the Muse. That's a spectrograph, and we're going to talk all about spectrographs next week. That's not actually there really to give you just this picture. It's supposed to analyze the different wavelengths that you have in this picture. And as you can probably guess from its size, that actually can get really, really complicated. And then finally, you have a fairly small thing that's right at the back of the telescopes that will do both spectroscopy and also just take you a picture. It can also do something interesting called coronography, which is where you have like basically like a little black dot in the middle of your telescope, and that's going to block out the light of the star. So if there's anything near the star that would be hidden by the light of the star, you can just put this dot there, and then you can see if there's something much weaker than the star in there. So this is just kind of as an example of all the stuff that's behind this. Usually what you have in there at some point are these CCD chips. So this is just an example of what Hawkeye uses. This is basically the same as in your camera or your phone, just a bit more fancy. But it's just a bunch of little pixels where if the light hits, it will produce a little charge, and you can measure these charges. Yeah?
Could you go back 2 slides?
Yeah.
That thing. What did you call that? Spectrograph?
Yeah, spectrograph.
Do you know where that one is?
It's in Chile. It's on the very large telescope.
And how many of those in the world are there? Do you know?
So, like this like usually, like all these instruments are like unique, or there's only 2 or 3 of them. But spectrographs are like very common. It's probably like the most powerful instrument in astronomy. If an astronomer sees something that he doesn't understand, first thing you want to do is take a spectrum. And next week it's going to be all about these. So they're very, very much used tool. So probably every big telescope has at least one of those. Okay. Now, great. So we now take we have our adaptive optics, we have our instruments, we get this really crisp picture, so we just take our telescope and just look at what we want to see, right? No, there is unfortunately a big problem that limits the best resolution your telescope can get, and that is something called diffraction. And that is, so if you have your wave coming here from the left, and you just send it through some slit. So this could, for example, be the opening of your telescope tube, or it could be also, you can also imagine you don't send it through a slit, you have a mirror here. It does the same thing. Now, what happens then is that it, doesn't just go straight. It also just kind of like starts spreading to the side. The same happens also if you instead of a slit, you have something blocking the path of the light. So here's, for example, with water, you can see there's a ship here, and you had waves come here from the side, and you can see them kind of curving around here. And then here you have them meeting up and interfering with each other. That's something that always happens with telescopes, because first of all, you have your mirror is only a certain size. But for example, you can have these, your mirror may not be perfectly continuous. So this is a test picture of the James Webb Telescope. So where they just pointed it at some fairly bright stars, and you can see these, these star-shaped rays coming up. What that's actually from is that from the fact that the mirror is made out of these hexagonal panels, and each of these will produce a diffraction pattern, and that's and that's basically why you have these rays. You can also see there's this additional ray in this star here. That's actually from these struts here that's holding it. So you always have these kind of diffraction patterns that are going to somewhat spoil your picture. Same happened with Hubble. So this is a picture from Hubble, and there you can see that you have these kind of cross-shaped ones. And that is, if you look, it's unfortunately kind of hard to see in this picture, but there's this mirror held in the middle here, and there's 4 struts holding it. And that's why we have these 4 diffraction spikes. And that's something that every telescope, yeah?
Can you get rid of these artifacts that are lit?
Yes.
Some software or
Yes, because you can fairly easily predict these, or you can just measure them, right? You just point your telescope at some bright star where there's nothing else really nearby, and then you know what this diffraction pattern looks like. So you know if for example, there's a big, like a somewhat bright object here, that's going to produce some diffraction pattern. But because you know that this object is here, you can calculate what this diffraction pattern is, and then subtract it from the picture. So you can remove it. And usually the pictures you're going to see will have these already removed a lot of the times. Like whoever's operating this telescope will already do this. But the problem is you can, like these, diffraction spikes, they're fairly easy to remove, but this diffraction also puts a fundamental limit on the best resolution you can get with a telescope. Because if you imagine, so you have your you have your wavefront coming in here, you're going to have some stuff kind of leaking out from this side of the slit, and you can have some stuff leaking from this side, and it's going to interfere, and it's going to produce this thing called an Airy disk. So if you had what's called a point source, like a extremely, extremely small light source, it will still produce you some blob of a certain size. Now, fortunately, if you have a larger opening, this blob gets a lot smaller. And one of the reasons you want a really big mirror is, one of them is you just collect more light, but the other one is it will make these diffraction patterns smaller. But it will still limit what you can resolve. So if you see you have your, you have 2 point sources, so 2 very, very small sources. Each of them will produce this diffraction pattern. Now, if they are far enough apart, that's fine, right? You can still see that there's 2 things here. If you move them closer together, they will somewhat blend into each other, but at some point, you can still kind of see that there's 2 different ones here. If they're too close, then they will just look like a single object, and that is fundamentally going to limit how small of an object you can still resolve. And if you want to calculate what is this diffraction limit, there's something called the Rayleigh criterion, which is just says that your resolution, also the angular size of this object, that's going to 1.22 times the ratio between the wavelength you're using and the opening or the diameter of the mirror you're using. And now, if you have some object that is some distance away, then you can calculate what is the angular size it's going to have. If it's really far away, which in astronomy it probably is, then this angle is going to be the ratio between the size of the object divided by the distance. So from this, if we combine these, we can calculate if we have a telescope and we have something that is a certain distance away, how big does something have to be so we can still resolve it. And resolve means that it just doesn't, like, that we can tell that it's, for example, if it's made out of two objects that are really close together, we could still say that there are two objects. So if we take, for example, we want to look at a nearby star with a very large telescope. It has an 8-meter mirror, so wavelength, for example, can have like a micrometer. And just take a light source that's about 10 light years away, so that's a fairly near-ish star. So the closest star is about 4.5 light years away. So this is, not quite the closest star, but still kind of our neighborhood. Then, if we want to resolve something, or then it would have to be at least 1.4 times 10 to the 10 meters large. So that is a 1 and a 4, and then 9 zeros behind this. So that's pretty big. So for comparison, the size of the sun is about a tenth of that. So if there was a star like the sun there, it would look, it would look 10 times as big as it actually is. If there was something, we could not measure the diameter of the sun because however big it is, if it was twice as big, it would still, because of this refraction, it would still have look like it is 1.5 times. It would still look 10 times as big as it actually is. Even if you compare to something like the distance between the Earth and the Sun, so that's about 100 times the diameter of the Sun. So that's 10 times as big as the resolution we have. So we could actually distinguish the Earth and the Sun. We could resolve this. But if our star was just 10 times as far away, already we cannot even see that. So if you want to look at things that are far away, very quickly you're just not going to be able to resolve stuff because it's just going to look too small to actually see. And so a lot of the time you're going to need stuff that doesn't require you to resolve that stuff. So next week we're going to talk about probably the most important way to do it, and that is you just try to look at the different frequencies of light and you get something like this. And next week we're going to see what this can actually tell you. Okay, questions? Yeah.
The $10 billion telescope. What was the name of that one?
Okay. I'm going to repeat the question because apparently the microphone in the room doesn't pick up audience questions. The question was where is it? Where is it? What this telescope was called. That's the James Webb Telescope. James Webb Space Telescope. Yeah, that was launched, I think, 2 years ago or something. And it was famously took like 10 years longer than anticipated and went. I think originally it was supposed to cost like $1 billion or something. It went ridiculously far over budget, unfortunately.
It has a lot of mirrors, doesn't it?
Yeah. So another problem was like this mirror is actually bigger than what you can fit into the payload of a rocket. So you actually had to fold it. So you have these individual segments, and some of them had to be like kind of folded back behind it, and then you unfold it. So that's one of the reasons these are in these individual segments. Yeah?
Okay, that's what my question is. What are the cost components that make such differences in the cost of the various methods? We got different 187 versus 110. What are the components that are making the primary difference?
Okay, so question was, where does this difference in cost between space and ground telescopes come from? So there's a couple of things. One thing is, if your telescope on the ground, a lot of the stuff you just don't have to build, like power communication stuff, right? That's something you just have a power line, or you have like an Ethernet cable or something. For a space telescope, all this has to be on there. You also have to have very strict weight limitations. So, these telescopes the really big ones, they weigh like several tons. And with the Space Telescope, you always want to have it as light as possible. There's also, space is kind of a really hard, like, it's not a comfortable place to live, right? So there's like cosmic rays you have to shield it from. You have to look at, the temperature can vary widely. You also want it to be really sturdy because you cannot just go there and repair it. I mean, basically everything is harder to do in space. Does it answer your question? Or?
Well, one would think that the cost would be reduced the longer we're doing this, but the costs are going up astronomically.
Well, so, I mean, this, when Hubble was built, like, you could not do this. Like, part of it is they're getting more ambitious. Like, this is, I mean, if you compare the size of James Webb to Hubble, like, this is a big, big step. So it's part of it why they're getting more expensive is also because they're more ambitious. Like, building something like Hubble would be a lot easier now. Yeah, all the way in the back.
Could you elaborate on the image you had earlier, the William Parsons image?
This one?
Yeah, what was it again?
Oh, okay. So the question was what this image on the right is. So this is William Parsons was one of the first people he was not the discoverer of the Crab Nebula, but he was one of the first people to really like study it. And this was like one of the first detailed drawings of it. And so this is, for the people that were into astronomy in the days, this is what people would see in the books back then. And someone thought this looked like a crab, and that's where the name came from.
Was it the comet?
No, this is basically the same thing you see here. It's just a big problem is that his telescope wasn't as good, and he had to look through it with the eye. So some of the more faint stuff he just wouldn't be able to see. So that's why it looks quite different in his drawing. But it's the same thing.
The dots are other stars.
Sorry?
The dots that you see there, they are other stars
These?
in the space?
I'm not sure. I don't know. I don't think they probably shouldn't be. I think if there were other stars, like he would have recognized that they couldn't be part of this and probably wouldn't have drawn it. But I don't know, to be honest. Yeah.
Question, and I think probably everybody else is going to be asking you sooner or later. Are your slides going to be available on the website?
Yes, slides will be uploaded.
Are your presentations being recorded?
Yes.
In some way?
Yes, we're being
They are.
recorded, and
Those
it's going.
are
Yeah.
also going to be available.
Yeah, it's all going to be up there.
Thank you very much.
Okay. Yeah.
How fast is Crab Nebula expanding? It's been 1,000 years, but it's like it's going at a breaking clip.
I mean, it's massive. So I can't tell you a number, but it's
Fraction of the speed of light?
It's definitely a lot faster than the speed of sound. And that's actually going to be really important in 4 weeks, or 5 weeks. It's probably this was a supernova. In the early stages of a supernova, it is a decent fraction of the speed of light. It's probably slowed down since then, but I would have to look it up. Yeah, behind.
I assume the resolution problem you talked about puts severe limits on our ability to see exoplanets. Is that correct?
Yes. So the question was if this resolution limit limits us seeing exoplanets. So there is actually a way around this resolution problem that I'm going to get to at some point. That actually, hang on, I have to go all the way back. Okay, so this is like the complete Very Large Telescope, and there's 4 of them. You can actually get around this resolution image if you combine all these. And people have done that, and they've been able to see some exoplanets directly. But they have to be, first of all, they have to be fairly close, and they have to be fairly far away from the star that you have. So there are a few exoplanets you can directly see, but the vast majority of them you can look at the spectrum and see them from there. There's different ways. We actually get kind of touch on one of them next week. So usually use the spectrum for that. Yeah?
Just thinking, would it be possible to put, I don't know what kind, but some kind of telescope in each of the Lagrange points, because something's there, it doesn't move, and then connect them for a real long baseline telescope?
Okay, so the question was, could you put telescopes to the Lagrange points, and then also could you put them into, could you do a long baseline interferometry with them? So I'm going to talk about long baseline interferometry in a couple of weeks. So James Webb Space Telescope is actually in one of the Lagrange points. So you can put telescopes there. Now, for interferometry, these days, if you want to do it over really long distances, that's basically only possible with radio. Which, I mean, you can do from space. There has been a Russian space mission where they put a radio telescope in Earth orbit to try to do interferometry with that one. I don't think it worked very well. The problem with radio telescopes in space is that radio telescopes have to be pretty big. And then you have the problem again that you have to somehow fit it on a rocket. So, like, in principle, it would be possible, but it would be kind of from an engineering perspective, it would be really hard. Yeah?
You mentioned earlier the charge coupling device or sensor.
Yeah.
Are those the devices used for detecting exoplanets by counting the decrease in photons coming from a star that's been temporarily blocked by planets?
Yes, for example. I mean, so there's a lot of telescope, or I would say probably the majority of telescopes have a CCD sensor somewhere in there. You have, if you want to do imaging, that tends to be CCDs. And of course, you can use them, for example, to do exoplanets. So yes, that is one of the ways you could use them, but also for a lot more. Yeah?
A short question. Where is the Very Large Telescope?
Okay, question was, where's the Very Large Telescope? It's in Chile, in the Atacama Desert.
And this is your introduction. Are you an astronomer or you're a physicist?
Yeah, so I am a physicist. I'm doing detection of ultra-high energy neutrinos, so neutrino astronomy, basically.
And I'm wondering, why are you at this university? We don't have a telescope, unless we still have your case.
So, okay.
Connected to your case, or?
Okay, question is, why am I doing astrophysics here if UChicago doesn't have a telescope? So,
Is this a good place for you?
it is. So, okay, what I'm personally doing, I would say, is I'm more on the detection side. It actually kind of leans a little more in the particle physics side of astroparticle physics. But there is a lot of astrophysics at UChicago. And part of that is kind of the days where you have your telescope right at your university are kind of over. Like, you wouldn't want to build a telescope in Chicago because, I mean, you cannot even see the Milky Way from here, right? So the way it usually works is you have your telescopes somewhere out there, and then you use them there, and then the data gets sent back. Or a lot of the time, the way it works, you actually, like, you don't own the telescope, but you can write proposals to, I want to see this object, can you give me the data? So, for example, like for James Webb, that's technically usable by anyone. Like, you can submit something, they're going to be reviewed, and if the people running it think that your idea of what you want to observe with it is good, then they're going to look at it and send you the data. So you don't really need your own telescope anymore most of the time.
Do you know, is this university connected to the Yerkes up in Wisconsin? Or have you heard of that?
Yeah, so I mean, Yerkes is not used for astronomy anymore. It's more like a historic thing. But there are some people from the University of Chicago still involved with that. For example, a big thing they're doing is these old film plates, where they have there's like hundreds of thousands of these little plates of observations they did, and these are being digitized and conserved. There's still some involvement.
One last little question. Have I seen from 57th Street, do I see a telescope film on this building?
Okay, question was, is there a telescope in UChicago? Yes, there is. There is an astronomy club. I'm not a member, so I haven't seen the telescope. I know some people who are in there, but yeah, it's a small one, but it's not actually used for research. Okay, yeah?
How long does it take for the signals in the telescopes in space to get back to Earth?
Okay, question was, how long do the signals from the telescope take to get back to Earth? So depends a lot on where the telescope is. So Hubble is low Earth orbit, so that's less than a second. James Webb is at one of the Lagrange points. That I would have to look it up, but it's probably a couple seconds. So like distance to the sun is about 8 minutes of light travel time. Lagrange point is not quite that far, so I would guess it's a couple minutes. Okay. Okay, I don't see any more questions, and thanks for coming.